Hello. Welcome to our sixth lecture on the design of probability theory and its uses. Uh, Last class, we saw how we could update from prior probability distributions to posterior probability distributions when information in the form of data was provided. So what I want to do today is first briefly recall what was involved in that updating, and then I want to discuss examples so that you see how this mode of reasoning is actually applied and how useful it can be. Very good. So what we saw last time is that we wanted to uh, make inferences about a quantity theta. Oh, at this point, I better bring my tablet. Very good. So we wanted to make inferences about a quantity theta, and so our starting point is we have some prior. We want to collect data and we want to update this prior. Um, we want to collect data about another variable that we're going to call x. Clearly, if we're going to make inferences about theta on the basis of x, there must be some connection between the two. There must be some relation. That relation is expressed in terms of the likelihood function. How theta affects the probability of x. So clearly what our prior really is the joint distribution uh, of x and theta. Now we can clearly use the product rule and re-express this joint distribution in the form of qx and then q theta given x. Very good. So where does the updating happen? The updating happens when we realize that what we are interested in is in the joint posterior, which we can write as the probability of x multiplied by the probability of theta given x. And the updating starts happening when we realize that we collect data x prime. So we say this joint probability, the joint posterior, is constrained to tell us that now we know the value of x, it's supposed to be equal to x prime. Furthermore, that leaves this other second factor in the product completely undetermined. So we need another principle that tells us what to pick for this. So here we use this principle of minimal updating. That's when we're really doing Bayes, and we say that whatever the probability of theta given x we had in the past, we're not going to modify it. We're going to keep all those beliefs that are not affected by the new probability. And so here we're going to write this as q theta given x. We did not update. So the updating is kind of funny. It consists of a piece we do update, and then it consists another piece that in which we keep everything the same. Because this is 0 unless x equals x prime, we can write this as x prime. And what we have here then is that if we integrate over x, this is very easy because this is a delta function, what we obtain is that p of integrate over x, we marginalize x away, we obtain the new posterior for theta, which is what we really want, which ends up being q theta given x prime, which we can also write as q theta. We can write it using this version here, q x prime given theta, all divided by q x prime. So here we have here we have Bayes rule, and this expression here, the equality of the second and the third terms, this is what is normally called Bayes theorem. Very nice. So let us see how we apply this. Basically, the idea is going to be we have some prior beliefs about theta. We multiply by these factors that include the data, and we obtain a posterior belief about theta. So let's see how this helps us reason about probabilities, about any problem. So here's an example. I'm going to do several examples here. The first example is going to be several examples actually that happen to be kind of relevant. The first is going to be testing positive for a rare disease. How do you analyze those probabilities? The second example is going to be about quantum gravity. And the third example I'm going to be doing is what happens when the data that you collected, you're not too sure about it, right? You're not sure about whether here you should put a delta function or not. In fact, you're sure you shouldn't because you don't really know what it is that you have collected, okay? So those are the three examples I want to tackle. Let us go for the first one then. Testing positive for a rare disease. So here's the background. You take a test, and the test for cancer comes out positive. For cancer, I'm going to use the letter C for cancer, is positive. And I'm going to use the letter Y for being positive. So the big question, should you panic? Well, you start collecting information. This is one of those cases when you get the data first and then you have to think about it, right? Should you panic? You find out that the test is actually pretty good. The probability of yes, the probability that the test comes out yes, given that there is cancer, is very high. Oh my God, then maybe you should really panic. Let's call this number A so that we don't have to write 0.99 all the time. So should you panic? And then you start thinking, oh, well, let me see. What I really want is the probability that I have cancer given that the test was positive. And now if you studied a little bit of Bayesian inference, that's what we are doing, you know for a fact that this is not the same as PYC, which would be pretty bad because after all, this is 0.99. So let us then try to compute PC given Y. The actual expression is given by Bayes' theorem. And it actually goes like this. The probability of cancer given Y is going to be, I'm going to use the prior here, QC given Y. QC. This is the prior for cancer. Now we're going to put the prior that cancer. Maybe I should have been using here Q's like that. Q y given c. Yes. And then all divided by q of y. Very good. So when we look at an expression like this, you say, okay, yeah, here we have this term that's actually pretty bad, 0.99%. But this is one of the great advantages of Bayes' theorem. Not only it allows you to reason, it tells you what it is that you should be asking for. So what we need here is, what is the probability of there being cancer irrespective of whether the test came out positive or negative or whatever, right? Just what is the probability? So we need that prior. So let QC be just the incidence of cancer in the general population. What is the percentage of people that have cancer in the general population? Well, let us assume it's a rare disease. So I put 0.01, 1%. That would not be very rare, right? But still, it's a small number. That's the point I'm trying to make here. Incidentally, that's probably the incidence of COVID, right? Anyway, 0.01. So we have this number that's 0.99, but now you see that the number you really want is going to get multiplied by 0.01. So now we need to know what is this QY that appears here. Well, QY does not depend on C or not C. QY is just a normalization. So what I'm going to do is I'm going to use the fact that Q of C given Y plus Q of not cancer given Y has to be equal to 1. Q of C given Y is given by, well, C given Y is going to be given by Bayes' theorem. So this is going to be Q of C, Q of Y given C divided by the normalization. Plus, for this one, we can also use Bayes' theorem. Q of not C given Y. Q of not C. Q of Y given not C divided by the normalization. And you see what the normalization is, right? The normalization. Come on, move. There you go. The normalization is the QY that appears there. So what this is telling us is that the normalization is going to be equal to QC multiplied by this rate, the probability of true positives, which is A, plus the probability of not cancer in the general population. So this is 1 minus QC. And then this is the probability that if you do not have cancer, you still be positive. So this is the probability of false positives, right? So let us assume, for the sake of argument, that this is the probability of true positives is A. The probability of false positives is 1 minus A. In other words, that the probability of true positive is A, the probability of false negatives is A2. So here we go. N is given by this expression. So now let us substitute back here. And here we have the probability of cancer, given that you tested positive, is going to be the probability of cancer, that's the prior, the probability that if you have cancer, then it's going to be positive, which is A, divided by QCA plus 1 minus QC 1 minus A. So substitute the numbers and you have 0.01 times 0.99. The test is really good, but the rest disease is rare. On this side you have 0.01 times 0.99 plus 1 minus 0.01. So this is 0.99 times 1 minus 0.99, 0.01. Obviously, I chose the number so that it gives a simple answer. So here we have a reply to what is the probability of cancer given that you had a positive result. It's 1/2. So good news. It's not 0.99. Here on this side you have 0.99. On that side you have 1/2. So does that mean that the test is useless? No, the test is not useless at all. The probability went from 0.01, the probability of cancer. Once you collect the test, it went all the way to 50%. So from 1% to 50%. But it didn't go all the way up to 0.99, right? So what this is telling you is that, yes, indeed, the information in the data is important. The information in the prior is important. And the information in the prior that we normally call the sampling distribution or the likelihood distribution, that is also important too. All of these factors matter. Very good. Did you see that the confusion arose, or possibly the confusion arose from confusing the probability of C given Y and the probability of Y given C? It's very easy to confuse those two. The confusion is normally called the prosecutor's fallacy. Which goes like this. I'll write it out because this is how prosecutors can swindle you. We know that if the defendant is guilty, there must exist evidence. No problem there. Here is the evidence. This is the data, right? Here is the evidence. Therefore, the defendant is guilty. Sort of amusing. One of the important approaches to the theory of probability, to the theory of inductive logic, of trying to reach decisions on the basis of incomplete information, was developed in courts of law, in jurisprudence, in the Middle Ages. This is the kind of thing that these guys started to figure out. So, pretty smart people back then. Therefore, the defendant is guilty. So notice what's going on here. We are saying we want to know, should I write P or Q? Well, anyway, we want to know the probability of the defendant being guilty, given that there is evidence, a smoking gun. What we actually know is that if the defendant is guilty, there must be some smoking gun. And we say this is equal to 1. This is very reasonable. What is not reasonable, so this is evidence. What is not reasonable is to set the two equal to each other. We know that if the defendant is guilty, then, or let me write it better, if the defendant were guilty, then there must exist evidence. Here is the evidence, you collected data, therefore the defendant must be guilty. This is not true. Of course, we know that the correct conclusion is to say that if there is evidence, the probability that the defendant is guilty, given that there is evidence, is going to be the probability that the defendant is guilty in the absence of evidence multiplied by the probability that, given this, that if he were guilty, or there would be evidence, all divided by the probability of the evidence being there, irrespective of whether this fellow is guilty or not. Just the evidence is there. So clearly you see the distinction here. If the defendant is guilty, of course there is going to be evidence. But if there is evidence, this person could be guilty, or somebody else might be guilty, or nobody might be guilty. Maybe the evidence appeared there totally by chance. So you have to take all of those things into account, and those are the things that are taken into account by those factors. So beware of fast-talking prosecutors. Let me give you another one that's sort of like interesting, another example. Here is a real example. Testing for quantum gravity. Let's write it out. So let's give you some background here. The interesting issue here is that while we do know that for most of physics we need to use quantum theory, it is not at all clear whether gravity itself should be quantized or not. Some fields in physics require quantization. For example, the electron field, the quark field, the photon field, the gluon field, all of these fields require quantization. But the temperature field, when you have a system that has a distribution of temperatures, there is such a thing as a temperature field. The temperature field does not need to be quantized. The pressure field, you have a fluid, pressure's there. The pressure field does not need to be quantized. So some fields require quantization, some other fields do not. And so the big question is, how about gravity? Given that we have not been able to produce a good theory of gravity yet, it's a relevant question. Maybe we've been trying to quantize the wrong thing. So in 2017, a few papers appeared. You see, okay. Another piece of background information. Since quantum gravity effects are supposed to be very, very tiny and very difficult to observe because the Planck length is so minute, so small, everybody is trying to seek pieces of evidence for quantum gravity that might actually be accessible to experiment. In 2017, two collaborators here, two groups of people, Chiara Marletto and Vlatko Verdal, who are theorists, proposed an interesting experiment that suggests that maybe we can test for quantum gravity doing fancy experiments, difficult to do, and yet doable within maybe the next 5 to 10 years. So this is important. Simultaneously and independently, Sogeto Bose and a large group of people suggested similar experiments. These guys are experimentalists, and so they really studied the possibility of doing the experiment in reality, right? The idea would be to study. So if you want to study uh, quantum gravity, okay, a little bit more background. And then some other guys, Michael Hall and Marcel Reginato, suggested that maybe these guys are wrong, and that these guys are also theorists. So there is a fair amount of confusion, but the stakes are very high, because if you manage to show that indeed you have to quantize gravity, then you go proceed in one direction. The moment that you start saying maybe you don't have to quantize quantum gravity, then the theories have to go in a different direction. And so the idea that what people noticed or had noticed is that when you have a quantum field, so for example, the electromagnetic field must be quantized. One of the reasons, or one of the pieces of evidence for this, is that if you had a purely classical EM field, does not induce entanglement. So a purely classical electromagnetic field does not induce entanglement. And if we do know something about quantum mechanical particles, is that they do get entangled by electromagnetic effects. For example, the helium atom. Example, the helium atom. Say even in the ground state, you have an electron with spin up, another one with spin down, and you have to worry about these guys being in a singlet state or being in a triplet state, and these things make a difference. So it's clear that the electromagnetic field can be entangled. So now the question is, will a gravitational field entangle things? Because the gravitational interaction is so weak, in order to enhance the probability of there being an effect, you have to study particles that are relatively large. Now, particles that are relatively large do not suffer quantum effects so easily, so it's a trade-off. So you go for mesoscopic particles that have maybe 10 to the 18 or 10 to the 15 particles, like a colloidal particle, and you have to bring them sufficiently close. Problem, if you bring them sufficiently close, then van der Waals interactions may actually enter the picture, and so you have to be close enough that the gravitational forces may become noticeable, but not that close that they might be overcome by van der Waals interactions. This is why the work by these guys here is particularly nice, because they realize that van der Waals interactions decay very quickly with distance, 1/6, while gravitational forces decay only as 1/r. And so there is an interesting window there to say you come close enough to get gravity, but not close enough to get van der Waals, and the particles have to be large enough to be gravity, but not large enough that you kill quantum mechanical effects. So it's a tricky one. But tricky experiments are not necessarily undoable. Gravitational waves have been detected, and so it could be doable. Very good. So what these guys are saying is, if we detect entanglement due to gravity, gravitational entanglement, then gravity must be quantized. Notice that what's being asked, what's being said here is that what we want is whether gravity must be quantized, quantum gravity, given that there is gravitational entanglement, right? This is what we want. You observe gravitational entanglement, must gravity be quantized? But this is not the same as what we actually know, which is that if gravity is a quantum theory, if gravity must really be quantized, then what is the probability of observing gravitational entanglement? If gravity is quantum, there will be entanglement. Very good. So we know that this is true. The mistake consists in writing that these two are equal. Of course, they are not equal. What we have is that the true assessment is that the probability of quantum gravity, which is what we do not know, given the fact that you observed gravitational entanglement, should be the probability Q of quantum gravity all by itself multiplied by the probability of gravitational entanglement given quantum gravity, which is what we assume to be 1, all divided by some normalization, which is the probability of gravitational entanglement by itself, whatever it is. It's a normalization factor. That's what we want. Because we have these extra factors here, all we can say about this is that whatever probability you had for your prior probability that gravity must be quantized, whatever you had before, now you're going to be doing better. Because after all, whatever there is down here is going to be less than 1. It's going to be contained somewhere between 0 and 1, less than 1, so you're dividing by this g here. So in a sense, what this says is that, look, if you do observe a gravitational entanglement, you increase the probability that gravity has to be quantized. But really, we do not know by how much because we have no way to estimate that. What's the rate of false positives, right? We don't know those things. Very good. So be careful when you say, people say, oh yeah, you're going to draw this conclusion. No, you don't draw that conclusion. You say, well, the observation of gravitational entanglement corroborates or enhances the probability that indeed you have to quantize gravity, but you do not know if that's significant or not. However, there is another thing that we can actually do, which is, suppose that we were to write the probability of quantum gravity. So this is where it gets interesting too. The probability of quantum gravity, given that you do not observe entanglement. If that is the case, this is still going to be the probability of quantum gravity, the probability of not observing quantum gravity, given that gravity is quantized, and divide by Q G E. Now this is interesting too, because if this factor up here is equal to 1, then this factor down here is equal to 0. So what this means is that if what you observe is that there is no entanglement due to gravity, then gravity itself cannot be quantized. So the conclusion here is something like observing gravitational entanglement does not imply quantum gravity. However, observing that there is no gravitational entanglement implies that gravity is not quantum. That implies that quantizing gravity is just a bad idea. So I hope you see how these ideas of using Bayes' theorem just purely for the purposes of reasoning can actually be extremely useful, even in situations when you don't really know what all the factors might actually be. It just tells you in what direction you're doing, what it is you need to figure out. It provides guidance to your reasoning. It's a win-win situation. Very good. Let me see. Time to stop here. I'll come back in a little while and give you yet another couple of examples.